Beats is the word physicists use to describe the characteristic loud, soft pattern that is heard when two nearly but not exactly matched frequencies are added together. So when these two frequencies are added together, it would look something like this. So let's check out what it would sound like and what it would look like to observe beats. With this simulator, there's a couple frequencies we can hear. The red frequency is at 440 hertz. This is what the red frequency sounds like. And we can turn that off and listen to the green frequency. The green frequency is at 441 hertz, and here's what it sounds like. Now let's combine the two together, the 440 hertz frequency and the 441 hertz frequency. So you can hear that sound that gets louder and softer. That's called a beat. And notice one of these large envelopes goes by every second. So we have a beat frequency of 1 because there's one sound or one envelope that goes by every second. Now the green frequency is at 442 hertz and the red frequency is at 440 hertz. Let's hear what it sounds like when we play both of those frequencies at the same time. So now we're hearing 2 beats every second. Now the green frequency is 443 hertz and the red frequency is still at 440 hertz. Playing them at the same time sounds like this. Here's another example of a beat frequency. So this red frequency is at 15 hertz and this green frequency is at 16 hertz. That produces just one of these envelopes, and so the beat frequency is 1. In this example, the red frequency is at 14 hertz and the green frequency is at 16 hertz. So now we're getting 2 of these beats, so the beat frequency is now 2. And in this final example, our green frequency is at 16 hertz, while the red frequency is at 13 hertz. So now we've got 3 of these envelopes, and so our beat frequency is 3. So the equation for the beat frequency is to take the 2 frequencies, subtract them, then take the absolute value of that. The electromagnetic spectrum. So students are supposed to know that radio waves, light, X-rays are all different wavelength bands in the spectrum of the electromagnetic waves, whose speed in a vacuum is approximately 3 times 10 to the 8th meters per second. So if we look at the different wavelengths of the different segments of the electromagnetic spectrum, the longest wavelengths are radio, then microwave, infrared, visible, ultraviolet, X-rays, and gamma rays. If we look at their frequencies, they go from the lower frequencies of 10 to the 4th frequencies to the higher frequencies of 10 to the 20th. So the frequency in this direction increases, whereas the wavelength in this direction decreases. Now, the visible set part of it, we also need to know that right about here is the red frequency, then orange, yellow, green, blue, indigo, and finally violets. And likewise, we're supposed to know that in this direction, the wavelength decreases, and in this direction, the frequency increases. Polarization. Remember that light is basically a transverse wave made out of an electronic component or an electric component and a magnetic component. So let's just say that the red part of this wave is the electric component and the blue part of this wave is a magnetic component. Together, they produce a light wave. Now notice that they are each transverse waves and they only propagate in certain directions. The red is along the y-axis and the blue is along the z-axis. So the light bulb is our light source, and these two discs are called polarizers. And over here we can see the image of the light bulb. Now what I can do is I can, in this animation, turn these polarizers a certain way. Now notice that if I turn the polarizers so that they're parallel to each other, I get to see the image. But if I turn the polarizers in such a way that they're perpendicular to each other, the image goes away. So as was mentioned in the example previously, light is a transverse electromagnetic wave that vibrates. Polarizers filter the light so that it vibrates in only certain directions. An example of this would be polarized sunglasses that filter light. This effect is called dispersion. What we're showing here is a red laser beam that's going through, well, it's actually going from air through a glass prism. I can change the color in this simulation of the laser beam, change its wavelength and therefore its frequency by moving the slider back and forth. Notice that the amount that the laser beam bends depends upon its color. So as I move it over towards the red end, it doesn't bend nearly as much, but when I move it over towards the blue end, it bends more. If we look at it with white light, which includes all the colors, we can see how they bend at different angles. So to define dispersion, it's the refraction of light based upon its frequency. Different frequencies, and therefore different wavelengths, have different indices of refraction. Therefore, different frequencies bend at different angles. Red has a lower index of refraction. Therefore, notice it doesn't bend as much as blue light would. Thin films. Now, this is the effect of thin films, or these are examples. So, on a wet day or a rainy day, if you look out in the parking lot, you'll notice that there'll be these little oil slicks that produce these very interesting colors. That effect is called thin film interference. You'll also notice that it happens in soap bubbles and also on CDs. But before we discuss thin films in detail, let's look at what happens to waves at boundaries. In other words, what happens to the wavelength, frequency, velocity, and phase of a wave when it goes from a dense media to a less dense media and vice versa. Here's a physics fact. When a wave travels from one medium to another, the frequency remains constant. So I guess that answers one of our questions. So in this animation, let's look at what happens when a wave pulse goes from a thinner length of string to a thicker length of string. So there it goes from the thinner to the thicker. Let's check it out one more time. Now let's look at what happens when we go from a thicker length of string to a thinner length of string. So there goes the thicker length to the thinner. And one more time. When we go from a thinner length of string to a thicker length of string, that's essentially saying we're going from a less dense material to a more dense material. So this is the equation we would use when we're going through the thinner length of string before it hits this point there at the thicker end. So afterwards, we notice that this transmitted wave pulse went in that direction, and this inverted reflected wave pulse went back in the opposite direction. As we said earlier, the frequency remains constant, but this velocity decreases, this wavelength decreases. Notice that the reflected wave, this wave here, is out of phase, meaning it's inverted compared to our original wave, and the transmitted wave pulse is in phase. So this is the symbol I am using for out of phase, and this is the symbol I am using for in phase, as it relates to the original wave pulse. So when going from a more dense to a less dense material, once again we'll use this equation as the velocity equation before, and the same equation for the velocity after. So this is the more dense medium, and this is the less dense medium. In this case, once again, we're looking at thicker string and thinner string. Now, when we do this, we get, once again, the frequency remaining constant, but now since we're going to a less dense medium, the velocity is increasing after the wave transmits from the thicker to the thinner string. The wavelength, notice the wavelength is now increasing. The reflected wave is in phase, so in other words, it's in phase as compared to the original wave. They're both upright waves. And the transmitted wave is also an upright wave, so therefore it's also in phase. So one of the previous examples, we looked at a wave that went from a thinner length of string to a thicker length of string. That's similar to what it's like for light that goes from a material with a lower index of refraction to a material with a higher index of refraction. So in this particular example here, we've got this light that's going from air, which has index of refraction of 1.00, to a film that has a higher index of refraction. So it has a particular wavelength originally in the air, and it reflects out of phase because we're going from a lower index of refraction to a higher index of refraction. Remember, when that happens, we're going to get a wavelength that is out of phase. The transmitted or refracted wave is in phase. The equation we'll use to calculate the new wavelength will be this equation, where all we do is we take the original wavelength that was out here and divide it by this, the index refraction of the film. So, as is similar to the previous example with the thinner to thick string, the frequency still remains constant, the velocity decreases, the wavelength also decreases, as you can see in this part of it. Now that's for the refracted wave. The reflected wave is out of phase, right there, and the refracted wave is in phase, right there. Now, when we go from a higher index of refraction to a lower index of refraction, once again, the frequency remains constant, but now, as we look at the refracted ray, the velocity increases and the wavelength increases. The reflected ray, this ray here, is in phase, whereas the refracted ray, or I should say, the refracted ray is also in phase. So let's look at what happens when light goes from an index of refraction N1 that is less than the film's index of refraction, and the film's index of refraction is greater than the index of refraction N2. So here's N1, let's assume it's air, and we've got this wavelength that is incident upon it right at this region right here, or that point right there, and then some of it refracts and reflects. So here's the part that reflects. We're going from a lower index to a higher index, so it's going to be out of phase with the original ray of light. The refracted ray always goes in phase compared to that wavelength, and we'll get some reflection between the film and N2. I'm sorry, that's reflection, and then refraction out. So notice that these two, compared to each other, are also out of phase. So what does that mean? That means if we take this particular thickness and look at it and double it, or take that value and double it, it will equal m times lambda f. Remember, this is how we calculated out lambda f. That would mean that it is therefore destructive when m is equal to 1, 2, and 3, and so on. And if we look at twice the thickness and we plug it into this equation, we would get constructive interference when m is equal to 0, 1, 2, 3, and so on. Now this only happens when this value theta, this angle, is very small. Basically, so close to 0, it's virtually 0. Now, let's look at what happens when the index refraction of N1, the N film, and N2 are set up so that N1 is less than the index refraction of the film, and the film is less than the index refraction of N2. So we get this ray of light that would have a certain wavelength. It reflects again out of phase. The original wavelength changes along with this particular equation there, and then it refracts, but this time it's going to refract out of phase compared to that wave, because N2 is greater than NF. Because that happens, it refracts through out of phase. Now, both of these wavelengths are out of phase compared to this wavelength, but compared to each other, they're in phase. So if we've got the distance 2t, remember this is 2t, and some m times lambda f, again remember this is how we calculate out lambda f, then we get constructive interference when m is equal to 1, 2, 3, and so on. And then we would get destructive interference if twice the thickness is equal to m plus 1/2 times the wavelength in the film, where m is equal to 0, 1, 2, 3, and so on.